So today on a special edition of Kicked Up Chemistry with Professor Leonard, we have Kicked Up Physics with Pounce the Physics Cat is going to help us out. And we're going to experimentally analyze vectors to see if they actually do add together mathematically like it says that they're supposed to. These are very, very common introductory physics lab combining forces together. And I'm going to go through and show you how to use a force table, how to record your data, and then analyze the vectors to compare the resultant with the equilibrant. So the resultant is in one direction, the equilibrant is in the opposite direction, so they differ by 180 degrees, but their magnitude should be exactly the same, it's just an opposite sign. So stay tuned and learn if vectors actually do add together mathematically like theoretically they should. Okay, so today I'm going to show you how to experimentally verify whether or not vectors actually do add like they're supposed to. So we've got Pounce the Physics Cat keeping an eye on our force table here. So our force table, as you notice, there are 3 spring scales. I already zeroed them out because, of course, with a spring scale, in order to adjust the zero, you can slide this little metal piece up and down. And I've already pre-zeroed it out, and our force table consists of a piece of round pegboard with feet on the bottom, so that way these scales can go right in there. And we're going to use the Newton side. So each of these lines is 0.2 Newton, so we're going to go 1 digit beyond that, so that way we have 2 decimals. Now they're labeled A, B, and C. And what we want to do is, before we record any of these, is we need to make a marks and figure out where these 3 vectors are. So we have all the vectors are pointing in opposite or different directions from the same point. And so what you want to do in order to get these as precise as possible is I'm going to put the ruler right along that metal line, and I'm simply going to draw a line, and my scales are already labeled, so this is scale A. Without moving the paper then, I'm going to come over here, and I'm going to do the same on this one, and hopefully all of our lines will be fairly close at intersecting. And this one is scale B, and then finally we have scale C. And look at that, they all intersect in the middle. So this is scale C. And so now what I have to do is I have to record the values of A, B, and C on this paper for this trial. So with this one, it appears to be just a little bit beyond 3, not even close to being halfway between 3 and 3.2. So I'm going to call this 3.05 newtons. So this is our resultant. In this case, it's in opposite directions. It's holding it in equilibrium. So it'd be called the equilibrant, but you calculate it exactly the same way. Over here, this one is smack dab on 2.6. So I'm going to call this one 2.60 newtons. And then on scale B over here, this one is 1.90 newtons. So once I take that data, my experimental data, then I have to go through and I have to start to analyze it. So I'm going to move this out of the way. Okay, now that I've gotten the force table out of the way, I've zoomed in a little bit, we need to find the angle between A and B, because the angle between A and B is going to then allow us to transpose that angle. And let me get a little closer here. And that is smack dab at 100 degrees between the two of them. So angle AB is exactly 100.0 degrees. Now, this vector was pointing in this direction, and this vector was also pointing in this direction. So they are acting upon the same point. We don't want them acting upon the same point. We want to draw them head to tail. So what I'm going to do is I'm simply going to transpose either vector A or vector B. It really doesn't matter which one you move as long as you move one to the end of the other one. And again, these are not to scale because this one is 1.90 newtons, that one is 2.60 newtons. So I'm just going to slide this down to this end over here, redraw vector B. There's vector B, and it is still 1.90 newtons. However, my angle has now changed, and it is the supplement of the angle. So since this one is 100 degrees, this one would be 80 degrees, 80.0 degrees, because a straight line would be 180 degrees. When we add up the interior angles, they have to equal 180. And so now we have our value here. And what we're going to do is we're going to find what would be the resultant. Now the equilibrant, this one here, it was holding it in equilibrium. If you imagine this one's in that direction, this one's in that direction, this one's in this direction. Imagine this was a slingshot and you had your rock right here in the middle and you were pulling this back. You're pulling it back with a force in this direction. If you were to release this, it's going to be shot off in this direction then. But because this one is 2.6 newtons and this one is 1.9 newtons, it's not going to go off exactly in that direction. It's going to shoot off in this direction. And that would then be our resultant. So our resultant and our equilibrant are equal in magnitude but opposite in direction. And so what I want to do here then is I want to find the resultant of these two vectors. Now, in order to do this, we already have the angle and we have two sides. So the easiest thing to do is to simply use the law of cosines, in which c squared equals a squared plus b squared minus 2ab cosine of c. And c squared then would be our equilibrant. A squared, doesn't really matter which one you call which, 1.90 newtons squared plus 2.60 newtons squared minus 2 times 1.90 times 2.60 times the cosine not of 100 degrees, but our supplement of that angle, 80 degrees. Now make sure your calculator is in degrees, not in radians. So I'm going to go ahead and do this part, and then I'm going to do this part and subtract it from it. So 1.90 squared plus 2.60 squared gives me 10.37. So 10.37 newtons squared minus 2 times 1.90 times 2.60 times the cosine of 80 degrees. Make sure you close the parentheses. That gives me 1.715. Newton squared. So that, of course, is equal to c squared. So 10.37 minus 1.7156 gives me 8.6544. And then, of course, we have to take the square root of that in order to get c. And c is equal to 2.94 newtons. So now we have experimentally found what our value for our resultant should be. And what we're going to do is we're going to compare that then to our experimental value for our equilibrant. Well, that is 2.94 and C is 3.05. And so it is pretty darn close considering we're using spring scales. I went one digit beyond that. This would round to roughly 3. This one's going to round down to roughly 3. But just to find the difference for sure, let's find the experimental error. And so the equation for experimental error is equal to the theoretical value minus the experimental value make sure you subtract those first, so you want to put parentheses around it, divided by the theoretical value times 100 to make it a percentage. So our experimental or our theoretical value is using a mathematical equation. What should you come up with? Well, mathematically we came up with 2.94 newtons. Experimentally we came up with 3.05 newtons. And the whole thing divided by our theoretical value, what we should get, 2.94 newtons times 100 to make it a percentage. And then you just type it into your trusty calculator, 2.94 minus 3.05, it equals, divided by 2.94, it equals, times 100, 3.74%. Now, I got a negative number, which meant that my experimental amount was greater than my theoretical amount, which is perfectly fine. If instead your experimental amount was less than your theoretical, then you would get a positive percent error. It really doesn't matter, because if you think of this as a number line, with here being our 0 point, if your 3.74% on this side of the line or 3.74% to the left of the 0 line, you're still off by 3.74%. So what you can do, you don't have to, but you can, is you can take the absolute value of this, and that way you always get a positive percent error, which is 3.74%. So again, considering that we have those metal rods were kind of bent a little bit from being used for years, the cheap little spring scales, a 3.7% error, I'm very, very happy with that. So from Pounce and I, thank you for watching how to experimentally find vector analysis.